We present our work entitled Panoramas from Photons, which enables the creation of high-quality single-photon planar reconstructions under fast motion and low light. Motion estimation from a sequence of images is a fundamental problem in computer vision. However, traditional methods are limited by what the camera can recover. In low light, conventional cameras will compensate by either increasing the exposure, thereby introducing motion blur, or increasing the gain and introducing noise. Here we see that for images with blur and noise, image registration, which is a common method used to estimate motion from images, does not work reliably. A possible way to overcome this issue is to use dedicated high-speed cameras. However, such cameras are not only bulky and costly, but also suffer from an extremely low signal-to-noise ratio. In this work, we instead focus on an emerging class of sensors called single-photon cameras. These single-photon cameras are capable of high-speed imaging in low-light conditions. Our prototype, shown here, can capture 100,000 frames per second. But there's a catch. Each captured frame is binary valued. A pixel is on if at least one photon is detected during the exposure time, and off otherwise. In the middle, you can see the raw frames captured by our setup. Notice that to show these binary frames, we have to slow down the video by a huge factor, and it still appears fast. On the right, we can see that any motion will cause a naive reconstruction, created by simply averaging neighboring frames, to be extremely blurry. In this work, we propose a stratified reconstruction technique capable of estimating rapid motion from a sequence of high-speed binary frames captured by such a single-photon camera. Once the motion is properly estimated, we can combine all binary frames into an image that is larger than the sensor's field of view, as shown here on the right. Here's how it works. We first capture a sequence of high-speed binary frames along some motion trajectory, represented here as the dotted black line. Think of each individual dash as a binary frame. If we knew this motion trajectory, we could compensate for it and perfectly reconstruct the scene from this sequence of binary frames. However, the motion trajectory is originally unknown to us, as shown here by the blue line. We started off by selecting contiguous groups of binary frames and naively aggregating them together to create the blurry images you see here. We then used an off-the-shelf registration method to localize these frames and give us a rough estimate of a motion trajectory. Due to the blur, the estimate might be very noisy, as shown here by the black lines. Nevertheless, we can use these noisy estimates to update our trajectory. And, at the next iteration, we select new groups of binary frames to merge together and use the updated motion estimate to work all binary frames. The resulting aggregate images are less blurry and will enable better subsequent localization. This process is repeated until we've converged, which, in practice, only takes a handful of iterations. For instance, here is a panoramic reconstruction after one iteration of our pipeline. Notice that there remains strong noise and distortions due to the incorrect motion estimate. After a second iteration, some distortions persist. And finally, after 3 iterations of our pipeline, we have a straightened panorama with little to no noise. As you can see, any registration errors or drift that occurred early on gets progressively corrected, leading to globally consistent matching. We can also create large-scale panoramas under fast motion. On the left, we show a video reconstruction of a scene played back in real time. Here it is again slowed down by a factor of 4. The panorama on the right was created with roughly 55,000 binary frames and captured in less than half a second. Contrast that to the time it takes to capture a panorama on your cell phone. We can also stabilize high-frequency camera shake. Again, we show the slowed down video reconstruction here to give a sense of just how fast this motion was. Super resolution is also possible thanks to sub-pixel alignment. The high-frequency motion trajectory, shown here in red, is also recovered. Finally, I want to show a quick example of when this method fails. Here we have a sequence shot at night and illuminated exclusively by artificial lights. Notice that our hardware prototype is fast enough to detect and even measure the flickering of artificial lights due to the electric grid. While this can be useful in its own right, it causes the underlying registration algorithm to fail as a key assumption of feature-based matching, namely brightness constancy, is violated. For more results, please see our paper. Thank you.